Hey there, science fans! Today we're diving into the exciting world of computer programming. At its heart, programming is just about giving instructions to a computer. These instructions are like recipes, and we call them algorithms. Imagine baking a cake. You'd follow a recipe, a specific set of instructions to make sure your cake turns out delicious. Algorithms are the same way. They tell the computer exactly what steps to take and in what order to solve a problem. Let's say you want to find the largest number in a list. An algorithm for that might be start by looking at the first number, compare it to the next, remember the larger one, and repeat until the end. See? Simple, right? By breaking down problems into smaller, manageable steps, algorithms make it possible for computers to solve all sorts of amazing things. From controlling traffic lights to predicting the weather, algorithms are the secret sauce behind the digital world we live in. So let's get cooking with some code. Now that we know about algorithms, let's talk about how we turn those algorithms into real-life computer programs. That's where the Program Development Lifecycle, or PDLC, comes in. It's like a roadmap that guides programmers from idea to finished product. Phase 1, analysis. This is where we figure out exactly what the program needs to do. Phase 2, design. With a clear understanding of the problem, we start designing the program. We decide on the overall structure, how the different parts will work together and what kind of data it will use. Phase 3, coding. In this phase, we translate our design into actual code that the computer can understand. We use programming languages like Python, Java, or C++, each with its own set of rules and syntax. Phase 4, testing. Once the coding is done, it's time for testing. We run the program trying different inputs and scenarios to see if it works as expected. If we find any bugs or errors, we go back to the coding phase to fix them, and there you have it. The program development life cycle in a nutshell. By following these phases, programmers can create reliable, efficient, and user-friendly software. So let's dive into the PDLC and start building something amazing. Remember how we talked about the PDLC being like a roadmap? Well, sometimes the best road trips involve detours and scenic routes. That's where iterative development comes in. Instead of completing the entire PDLC in one go, we break it down into smaller cycles. We might start by building a basic version of the program with just the essential features. Then we test it, get feedback from users, and make improvements. We repeat this process, adding more features and refining the program with each iteration. This approach offers several advantages: catching and fixing errors early, flexibility to incorporate new ideas, and keeping users involved. So whether we're building programs or houses, remember that iteration is key. By embracing flexibility and continuous improvement, we can create truly amazing things. Let's iterate our way to success. Section 4. The brain, the body, and the computer components of a computer system. We've talked a lot about software, but what about the hardware that makes it all possible? Just like our bodies have different parts that work together, a computer system is made up of several key components. The central processing unit, or CPU, is the brain of the computer. It's responsible for processing instructions and performing calculations. Memory, or RAM, is like the computer's short-term memory. It stores data and instructions that the CPU needs to access quickly. Storage, like a hard drive or SSD, is where the computer stores data and programs permanently, even when it's turned off. Input devices allow us to interact with the computer and provide it with instructions or data. Examples include the keyboard, mouse, microphone, and touchscreen. Output devices allow the computer to communicate with us, displaying or presenting the results of its processing. Examples include the monitor, speakers, and printer. All these components work together in harmony, allowing us to write emails, browse the internet, play games, and do countless other things with our computers. It's a beautiful symphony of technology. So let's appreciate the hardware that powers our digital lives. Section 5. From algorithms to actions, subroutines, and top-down design. When writing complex programs, we often break down those algorithms into smaller, more manageable chunks called subroutines. Think of a subroutine like a mini program within a larger program. It performs a specific task, like calculating the area of a circle or sorting a list of names. This approach is part of a broader strategy called top-down design. In top-down design, we start with the main problem we're trying to solve and break it down into smaller sub-problems. We then create subroutines to solve each sub-problem, continuing this process until we've addressed every aspect of the program. This approach makes writing and debugging code much easier. So, the next time you're tackling a complex programming challenge, remember the power of subroutines and top-down design. By breaking down problems into smaller, more manageable pieces, you'll be well on your way to building amazing things.